What we use for shielding is not lead or some other material that has no use, but simply the provisions, food, water, and things that food and water become as the mission proceeds are useful materials for shielding against solar flares. Solar flares were a terror for Apollo because Apollo was a dash out to the moon and back. They had very little provisions because, after all, it was only like a one-week mission round trip. And they were simply counting on probability to allow them to avoid the solar flares, where a typical solar flare might occur only once a year. And in fact, they did avoid them just by being reasonably lucky. The probability was, in fact, in their favor, but they could have been unlucky. They weren't. But Mars, simply because we're going to Mars and we're going to have 10 tons of provisions, including water, on the ship, that's plenty to provide shielding against the solar flares. Now, with respect to cosmic rays, which are frequently raised as a reason why we can't go to Mars, and cosmic rays are different than solar flares. They have energies of billions of volts, not millions of volts. They could easily go through 5 inches of water. We have already taken cosmic ray doses on space station missions comparable to what you would get on a round-trip Mars mission. There are a number of Russian cosmonauts that have taken cosmic ray doses that are fully equal to that which you would get on a badly designed, unshielded round-trip Mars mission. And there are American astronauts that have taken doses comparable to what you would get on a well-designed Mars mission. And we have observed no radiological, nor would we expect to, because these doses, even at the large end there, are only represent based on our knowledge of radiological health effects, about a 2% risk of getting cancer at some point later in life. And 2% times 6 or 7 people is still only a 1 in 6 chance that someone would have gotten a radiological disease, and none of them have. Now, we have observed zero-gravity health effects, but these can be avoided by spinning the spacecraft. We don't need a 20-year research program to figure out how to fly a two-body system, okay? And in fact, as people know, the Mars Society is going to prove this by flying a two-body system. The Tempo 3 program, a flight experiment, which we're going to do a balloon drop of this fall and fly in space next year, hopefully. But in fact, it's even been done by NASA back in the 1960s, the Gemini Agena program. They flew tethered spacecraft. But if you spin this up, you can create artificial gravity and you won't have the zero-gravity health effects. So, they're flying out to Mars on a 6-month trajectory. When they get to Mars, they cut the cable. This thing goes away into interplanetary space. They aerobrake into Mars orbit and then go land at site number 1, where a fully fueled Earth return vehicle is waiting for them. Now, we've been on the ground at site number 1 for 2 years. We've explored the areas with robotic rovers like the MER rovers that have taken pictures of everything. We know what the layout of land is. We have pictures from orbit of the place. We have a radar beacon on the ground to draw them in. We got an ace fly in this thing. We should be able to land right on the spot. And those of you who know your space history will know that during the Apollo program, we actually landed an Apollo lunar lander within 200 yards of a Surveyor robotic spacecraft that had been put on the moon a couple of years before. And we have much better guidance systems today. So we should be able to land right on the spot. But let's say we don't. Let's say we land 10, 20, 30 miles away. These would be very large landing errors under these conditions. We're still okay, because we have with us in the lower deck of the HAB a pressurized ground roving vehicle that, like a little 4x4 with a pressurized cabin, runs on a methane oxygen engine, and it has a one-way driving range of 600 miles. So it would really take piss-poor piloting to land outside of the reach of such a rover. But let's say that happens. Let's say they land instead of here or here or here. Let's say they land here or, there, on the wrong side of the planet. This would represent a serious problem with the pilot selection process at Johnson Space Center. If that happened, we can still save the mission because we got the second Earth return vehicle following them out to Mars. And if they do land over here, we can bring this one down to land near them wherever they did land. Okay, so And finally, as a fourth level of defense on the mission, if all this fails, if we can't land accurately, if we can't drive there, if we can't use the second ERV, fourth level of defense of the mission is we're on the ground, on Mars, no one's been left in orbit, we've got Martian gravity, we've got the significant defense against radiation offered by the Martian environment, and we got enough supplies with us to last for 3 years, so that if worst comes to worst, we just tough it out on the surface of Mars until more supplies and another Earth return vehicle can be fired out to us at the next launch opportunity. But let's say it works. We land here, Earth return vehicle's in good shape. What do we do with the second Earth return vehicle? We land it somewhere else. Well, we could land it nearby, just over the hill, but I prefer to land it somewhere else, a distinctly new site, but within long-range driving distance of the first site, perhaps a few hundred miles away. So it will make propellant that it will use to start to prepare for the next mission, which will go there to explore a new area, but it is available to the crew if necessary. So the crew will have available to them 2 complete Earth return vehicles, either one of which can take them home, as well as 3 habitable cabins, the big one in the HAB module and the 2 smaller cabins in the Earth return vehicles themselves. So they're multiply backed up. But the real purpose, of course, of the second Earth return vehicle is to make propellant to support the next mission, which will fly to it in 2018, along with another Earth return vehicle, which is their backup, but which otherwise opens up site number 3. So the idea here is that every 2 years we launch 2 boosters off the Cape, one to open up a new site, one to explore the previously opened site. 2 boosters every 2 years is an average of 1 per year to support a continuous program of human exploration of Mars. Now, when we were flying shuttles, and the shuttle program was actually functional, we were flying them at a rate of 6 a year. So we're talking about taking 1/6 of our heavy lift capability and dedicating it to exploring Mars. You know, I think that as long as we have a space program, it's entirely reasonable to take 1/6 of its heavy lift capability to actually explore space. And so this is something this country can certainly afford. So this, in fact, is an actual photograph of the Mars base. Okay, so here's the HAB module, tuna can HAB, upstairs for habitation, lower deck is sort of the garage for the little pressurized rover. Now, more recently, the Mars Society has been looking at exploration on the in the deserts in the Arctic with the ATV-type vehicles, equestrian vehicles, and those are extremely useful, and we'd probably use them as well. Here's the Earth return vehicle, the cabin, the 2 methane propulsion stages. The fuel producing unit is built into the landing stage, which acts as the takeoff pad for the rest of it. There's the reactor in the crater in the background and the wire that brings in the power. Here's some photovoltaic panels that have been set up in order to provide backup power if we ever have to turn the reactor off. We also have backup power available from running the engine in the car or the light truck or the ATVs. Then here is a little greenhouse. This is not a mission-critical element. It is an experiment in learning how to grow crops in Martian soil with Martian water, Martian sunlight, Martian gravity. The crew does not depend on it, but it's an experiment in learning how to do agriculture on Mars for the benefit of future missions and future bases. Now, we're going to be on Mars for 1.5 years. Why? Because that's the amount of time the planets have got to move around to give you a good launch window back to Earth. You could launch much earlier. You could launch within 30 days of landing. Those are your choices, either 1 year to 1.5 years on the surface or like 2 weeks to 30 days on the surface. But that's a larger delta V for the return, and you get almost no exploration done. And you actually end up spending more time in transit, significantly more time in transit. So you actually get a greater in-space radiation dose on that kind of mission, the short stay mission, also known as the opposition class mission. So the opposition class mission is frequently proposed by people who want to make the Mars mission look impossible because it runs up the radiation dose, it decreases the exploration time by an order of magnitude, it increases the delta V on the mission, so that increases the mass of the mission. It's not what you want to do. You want to stay on Mars for about 1.5 years, maximizing your exploration time. The figure of merit that you should use on a Mars mission is not minimum time away from Earth. If you want to minimize your time away from Earth, don't leave. Okay? The figure of merit for a Mars mission is person days on Mars divided by tons in Leo. And to do that, we do the long stay mission, to do a lot of exploration, we fly home. We leave the HAB behind on the surface of Mars. So each time we do this, we add another HAB to our system on Mars, whether it's a network scattered across the surface to enable exploration across continent-sized areas, or eventually, once we choose the best place to put a permanent base, start landing them all in the same place and develop the beginning of a first human settlement on a new world. There is nothing in this that is fundamentally beyond our technology. There is nothing in this now that we can't do.